Now that we have an understanding of what uncompetitive inhibitors are, let's take a look at our Michaelis-Menten plot. So once again, a Michaelis-Menten plot, on our x-axis we have substrate concentrations, and then on our y-axis we have our initial rates or our velocity values. Now, if we take a look at a normal progression curve for an enzyme with no inhibitor, we can see that we are approaching this asymptotic line, which is referred to as Vmax. So Vmax is the maximum velocity, or that maximum initial rate at which the enzyme is converting substrate into product. It's the maximum rate that it can do that. Now, initial rates, we can note, increase as substrate concentration increases. Why is that? We have to understand the theory behind that. So if I have an enzyme and I only add 1 mole of substrate, now that 1 mole of substrate, it has a diffusion time for when it reaches that enzyme. So that's affecting the rate at which the substrate is being converted into product. Now, if I had that same enzyme, but I added 2 moles of substrate, by the time this first one diffuses over to that enzyme and converts the substrate is converted into product, this second substrate will have some time to diffuse to the enzyme so that it's converted into product as well. So essentially, the more substrate that we have, the more saturated the enzyme will become with substrate. So if I have this enzyme and there's just a lot of substrate all around it, by the time the enzyme converts one substrate molecule to product, the other one will already be there to be converted into product. And that's why as substrate concentration increases, the Vmax value, the initial rate or the conversion from substrate to product, it increases. So essentially, we are just reducing that diffusion time, and we are approaching a constant time, and that constant time is just how long the enzyme itself takes to convert that substrate into product. So now that we understand what Vmax is, we can further understand how uncompetitive inhibition affects our enzyme's initial rate. Now, for uncompetitive inhibition, we can note that Vmax decreased, so our initial rate decreased. Now, why is that? So that's relatively straightforward to understand because a reaction rate is going to be directly proportional to the concentration of enzyme. If you have lots of enzyme, the substrate is going to be used up more quickly, and the overall reaction rate is going to be much quicker than if you have a very low enzyme concentration. Just imagine one enzyme doing all the work compared to maybe having 10 enzymes doing the work together. So you're going to have a faster initial rate. So Vmax decreases because when an uncompetitive inhibitor binds to the enzyme substrate complex, it renders this complex inactive. And since we are inactivating enzyme substrate complexes, we are reducing the number of active enzymes available to convert substrate into product. As a result, our initial rate will decrease. Now, once again, why is Vmax decreasing? Vmax is decreasing because we're reducing the number of available active enzymes because that inhibitor is inhibiting that enzyme. Okay, so now let's take a look at Km. So Km is our substrate concentration at 1/2 Vmax. So if this is my Vmax, this would be half of Vmax relatively. This is half Vmax. And the substrate concentration at half Vmax for a normal enzyme gives us our Km value. So this would be the Km value for our normal enzyme. And over here, for our enzyme that has the uncompetitive inhibitor bound, this is Vmax. So this would be relatively the halfway point, so 1/2 Vmax, and this would be the Km value, the substrate concentration at that point. So we can note that Km decreased. This was our initial Km, and Km decreased. Now, why is that? Why is Km decreasing? Well, in this case, we have to understand that there's a specific situation going on that is unique to uncompetitive inhibitors. So in uncompetitive inhibition, once again, we have that substrate, we have that enzyme, and the substrate and the enzyme combine together to form that substrate enzyme complex. And in uncompetitive inhibition, the inhibitor, it is binding to this substrate enzyme complex. In non-competitive inhibition, remember that the inhibitor can bind the substrate. So in non-competitive inhibition, the inhibitor can bind the enzyme by itself, or it can bind the substrate enzyme complex. But in uncompetitive inhibition, the uncompetitive inhibitor, it does not bind the enzyme by itself. It binds the substrate enzyme complex. And when it does so, it affects this equilibrium. And according to Le Chatelier's principle, if something is affected in the equilibrium will shift to circumvent that change. So if we add the inhibitor over here, we are reducing the concentration of substrate enzyme complex, so the equilibrium will shift to the right. Now, when we see this shift in equilibrium, this may come across as, okay, the enzyme, it must have a greater affinity for the substrate because Km can refer to affinity. So going back up here, a low Km value means higher affinity, and a higher Km value will mean lower affinity. So at first glance, when we see this, we may think, okay, Km is decreasing, low Km value, it means higher affinity, so the enzyme is gaining higher affinity. But that doesn't really make sense because the enzyme is being inhibited, so how will it have higher affinity for substrate? And when we take a look at this equilibrium, we can see that since we are reducing the concentration of substrate enzyme, this equilibrium is shifting to the right to circumvent that change according to Le Chatelier's principle. So that is essentially the Michaelis-Menten plot for uncompetitive inhibition. We can see that Vmax decreased and Km also decreased.